Okay, we should be recording now. Today I just want to take you for a brief look at our new product, Ennova Blue. Ennova Blue is an integrative CFD pre-processor, post-processor, and includes a version of OpenFOAM compiled for Windows. So normally in the past you've had to run OpenFOAM on a Linux environment. Now we're going to show you a solution that's based entirely on native Windows. So to get going, if you go to our support page and do download, you'll see download here for Ennova Blue. You can press that button and download Ennova Blue. Once you have that downloaded and have it installed, you'll be prompted to email a license information. The license information is the MAC address of the machine, and I can show you how to get that. So once you have an Ennova Blue installed, you'll have a icon on your desktop here, Ennova Blue. And if you open up that, and if you don't have a license, you can hit on a little blue Windows application menu here, go to Windows options, and if you go to license, you can go show host IDs. So what you need to do is just copy and paste that into an email and send it to us, and we will return a license. Once you get that license, you need to copy that to your Ennova Blue install directory, which is here, and you'll see a directory here, license, and you can copy in your Ennova license, and then you are installed for Ennova Blue. We offer short-term temporary trial licenses of Ennova Blue, and you'll get an email back with that license so you can explore Ennova Blue without having to pay, of course. So once you have Ennova Blue up and running, you'll see that the new Ennova now has a setup here, setup Blue CFD, and this is all the OpenFOAM setup for you. So I'm just going to take you through a very simple example today just to show you how it all works. We can start off with opening up a CAD file. This is just a pipe, and I'll give you a little bit of a tutorial on Ennova as we go, but there are many tutorials, this exact tutorial in detail, that you can follow online, either on YouTube or go to our website and Ennova University. So first of all, what I'm going to do is just take all these surface groups that came in from the IGES and move them to a group, and I'll call them pipe. So now we have everything here called pipe, and as this is a CFD analysis, I'm going to set up some boundary conditions. So I can move that group to inlet, and move this to inlet, and I'll call this inlet 1. We can also have an outlet. Move the group. And this is also a symmetry plane here, and we call that, say, symmetry. So that's our boundary conditions. You can see them here, inlet, outlet, but we don't have a computational volume. So in order to get to a computational volume in this case, we need to build the volume and repair the CAD. Like the CAD, if you have a look, these various surfaces, if I hide the surfaces, you can see it better. Typical IGES, the different surfaces are close, but there's two surfaces there. So if I pick this surface and look at the face, it's that one there. And if I pick this surface, it's that one there. So they're all kind of in the right place, but they're not stitched together. So in Ennova, we give you an automatic button here. We can just go ahead and press it to repair. And you can see now that all our red edges have turned black. Black is good. Black means that every face is connected, edge is connected to two faces. So everybody is stitched together, And you can see now we have a volume. This is our computational volume. This is where OpenFOAM is going to do its magic, do its CFD on. So that's our computational volume. Obviously we need to have a mesh to run OpenFOAM on. We go to the mesh icon and we can go to the global mesh controls. So generally speaking in Ennova, these are the three most important numbers that you can enter. The max size is the maximum size element that you can possibly want. In this case I'm doing 0.01. The min size is the smallest element that you want Ennova to look for. And refinement number, I'll do 12, means that if it's a circle, you're going to have at least 12 mesh points around the circle like ours in the clock. So now if we just do a little surface mesh of that just to see where we are, that's what we can control what we want to mesh. So we'll just mesh the surface first. And I'll take you through this one step at a time because Ennova can mesh the surface, the volume, do everything simultaneously, but we'll just do it one step just so we can see it. So here's our surface mesher, and you can see we've created a surface mesh now. And you can see that it's made elements down to like 0.05 there. So somewhere in between the min and the max size. So in order to honor all these constraints, that's the mesh we get. Now moving along, for viscous walls, we want to have a boundary layer type element. So I'm just going to do 5 of those. These are the layers, the 2D layers that we put near the wall to resolve the wall boundary layer. And I'll make the height, in this case we're meters, so I'll make the height like half a millimeter. Now, in order to grow prisms, we have to tell Ennova what we want to grow prisms on. So we go to a local thing, we can select this volume, and we can say, I want to grow prisms on the pipe. Turn that on, use volume. Use volume means whatever rule we said for the volume is going to be on the pipe. And the rule on the volume up here says it's global, so those are the global numbers we entered. So basically what we're saying is that those two global numbers, half a millimeter and 5 layers, are going to be. So just apply that, and so now we can grow the prisms. And you can see now that they have slid on the inlets and outlets. Let's see inlet again on here. Very, very coarse mesh, just to give you a demonstration. And you can't see any, and slid on the symmetry plane here. So we now have prisms and we now have the surface mesh, but if we do a section through the mesh, you'll see that we don't have anything in the middle. So we have to fill in this middle bit in the volume. We do that with this command over here. This is the fill in mesh, and the triangle and the hammer. And you can see polyhedral mesh is ticked. For OpenFOAM, we always use the polyhedral mesh. And so now here's our nice little mesh. And this is the difference between the, if you're wondering, why wouldn't I just use OpenFOAM with the open source mesher that comes with OpenFOAM. It's being able to create really high quality meshes like this that is what we bring to the table for OpenFOAM. So now if we take a little slice through it, you can see now we have filled in the volume with polyhedral elements. We have the ability to check the mesh in OpenFOAM. Orthogonality is important. You can see we're at 65 degrees for orthogonality, and skewness is for numerical accuracy. We're like wonderful below 1, so anything below 5 is is good. So very high quality mesh. At any point, if you have something nice, in case there's a lightning storm, which it is for me right now outside, you may want to save your work. Ennova saves the file as an ECF. It's called Ennova Compact Format or Compressed Format, and that's like our project file. So we have a nice mesh. Turn it on. The next thing is that we would like to set up OpenFOAM. And here we go, set up Blue CFD, what we call it. And if you're familiar with OpenFOAM, then these are all going to control the dictionary files. If you're not familiar with OpenFOAM, then these are just all the information that the CFD solver needs to work. So we start with this, and the version number, leave it at the highest version number that's available, which is 2412 in this case. We are running OpenFOAM 2606, but 2412 is the file format that we want to use. If you have to go back in time, we can allow you to go back in time, but leave it on the top one. We can run incompressible. We can run simple foam. I've got 4 cores on my computer, so we can run Scotch on 4, and we can leave all the settings. So it's going to run 1,000 iterations unless it converges. We can move over to the schemes. These are the schemes it's going to use to solve the differential equation, and leave those default. Again, this is the solution algorithms. We can see we've got various things, connectors and moment predictor on, and the different tolerances we want everything to converge. They're set to be reasonable default, so if you're not sure what to change them, if you leave everything exactly as it is, you should be okay. The material in this case, let's just do air, and we can see that it's a fluid, and for air everything is set up okay. And then we can go to the properties, and there's lots of different things that you can do here, you know, radiation, wave models, overset meshing, rotating systems. But in our case, we're just going to assign volume 1 to the fluid that we just assigned, fluid and air. We're going to use the K omega SST turbulence model and set some initial conditions. So that's our setup. So once again, just backing up here, we set the solver type and the control, like how long it's going to run for, what time step we want, the solvers that we're going to use, the algorithms to solve those solvers, the fluid type, and then our property, our volume, you know, assigning it to the fluid type. So the only thing left now is the boundary conditions. And you can see we have plus X going in this direction. So we can walk through our boundary conditions, and here they all show up here. You can see we've got an inlet. We can make that an inlet. And we can give it an X direction of 1, say 1 meter per second. General rule, much easier to work in SI, System International units, and the metric system. So OpenFOAM tends to have that by default. So if your model is in inches or your model's in feet or meter or something else, generally speaking, by the time you get to setting up OpenFOAM, you want to convert everything to SI. And so we can do 1 meters per second. We can go to inlet 1. Now inlet 1, of course, is this bottom guy, and he's in plus Y. So again, define him as an inlet, and we don't want it 1 there. We want, like, maybe, I don't know, he's pretty small, so 0.4 going up. So I've got 1 meter per second going left to right, and 0.4 meters per second little jet shooting in there. So then the outlet was a little green patch on the top. We can set that as a standard outlet in OpenFOAM, and we can see subsonic default. Just leave everything the way it is. Oh, sorry, I was talking too much. So inlet is an inlet, outlet is an outlet, subsonic default. Let's make sure we got that right. Yeah, inlet, outlet. And then pipe is a wall, no slip, that's just a standard boundary condition. And the symmetry plane is just a symmetry plane. So that's our boundary conditions. I have the mesh, I have my OpenFOAM setup all done. It's as simple as that. I can now save the file. So now all that's left is to run it. And this is where it gets really interesting with the Ennova Blue, because in the past we would export the geometry and then you would have to take that geometry. I'm working on a little laptop here. We have to take that mesh, OpenFOAM mesh system, and take it to a Linux machine and run it on Linux. So now for the people that are just running on a Windows laptop, we can extrude this. Here's my pipe. You can see I've got some other examples. I'm just going to make this E1 for the day, so we'll expect a directory here called E1. ASCII or binary, doesn't matter, that's how the files are written, we can do binary. And so now that's exported the files to that directory. So now we can then go ahead to running OpenFOAM, and the way we do that is we press this run button, and that gives us an environment to run OpenFOAM. Now this is where, so if I do a directory now here in this, you'll see I do have a batch file to run the whole process, but which is what we're going to do. But also too, you may want to, OpenFOAM is a collection of many hundreds, not maybe thousands, but many hundreds of commands to do various specialized features. So if you're doing rotating systems, ball bearings, turbine blades, you're doing anything that's moving mesh or overset, sometimes there's a very detailed set of procedure that you need to follow with different executables. Something simple we can do is just run OpenFOAM check mesh, and you can see we've set up the environment. So this is the OpenFOAM program that's run. I just ran it from the Windows, as simple as that, and you can see what it's told me about that, and it goes through and it tells me that the mesh is okay. That's the most important thing, is that to see this little word here, mesh okay at the end. So generally speaking, I always just run check mesh manually. The next step we can run is the actual OpenFOAM solver, and we can just run that as a Windows DOS bat command. And now you can see OpenFOAM doing its various things. It's running. It's a very small case. It runs super fast. And so you can see we ran simple, a conversion to 107 sections, and it finished. So that's like OpenFOAM, really exciting, 2606 running on Windows. Now we're not done yet, of course. Inside Ennova, you might want to have a look at the solution. Come to post-process. If we open up this, you can see on our directory E1 post.foam. There's a foam post-processing. And now we can see we're inside a post-processor. You can see it brings you to the last iteration that solved for 107. Look at the results, and we can do things like this. For example, we can color them according to, say, perhaps a U magnitude. And this U magnitude is the magnitude of the cell center. So it's not exactly on the surface, of course. For a viscous wall, it would be 0. But you can see here's our velocity. I'll make it so you can see the text. And you can see we've got velocity coming in here, a jet coming in here. Remember, 0.4 meters per second, so it's down on this range in here. And then the flow's having trouble turning, and it's really coming here, and then it's exiting outside. So we can take a look at, maybe we want to have a look at some vectors or something, just to be interesting. We can do it through a plane, vector U, and I'm not going to do presentation grid, I'm going to do CFD because I don't have a, and I can go apply. And that should give us, there we go, give us some vectors. You can see it's, if we turn off the geometry now, we'll turn off the symmetry plane, you can see, and the vectors may be a little big there, right? So we might want to just edit that a little, and scale factor and length, maybe make that 0.02. There we go. So now we can see our vectors turning the corner. And if we look closely in here, see it's struggling to sit against the wall. And of course I can turn off some of these other things, so we can just look at the... So if the run had run a little longer than what we expected, one of the other things we could have done, but we didn't have time to do because it was running too fast, I'll just show you, is we could have taken a look at the residuals under here and plot them, for example, and you can see that's what our convergence history looked like. So very, very nice converged. I'm just stepping down 1, 2, 3, 4, 5 or 6 orders of magnitude in convergence on everybody. That's what these lines are. So 1, 2, 3, 4, yeah, 5. So I'll stop here. Most probably I'll be the person who is connecting with you if you need support or help in getting going. But please take a look at our website, download it, and let us know what you think. Thank you.